All right, welcome back, class. This is Unit 9.2a, Exponential Growth and Decay Applications. So, for those who ask in class, Sean, when will we use this? This is going to be real-life applications directly. And if you did the extra credit activity, it has a direct correlation to that. So, there are real-life applications with math. The two models we're going to be looking at are a growth model and a decay model. So pretty similar to what we learned last week. And then the variables are associated to definitions. So in the growth model, you'll notice that we are adding here because we are growing in increasing rate. So A stands for your initial starting amount. R stands for your percent increase in a decimal form, so that's important. And then T is time in years, and that's the exponents to the T power, the power of T. And then in your decay model, it's minus, so you're looking at how quickly it decreases, the rate in which it decreases. And like I mentioned in the first lesson, this is like your depreciation of a car, the decay of the model. So we will be able to write an exponential growth model based off this this word problem here. It says a business had a $10,000 profit in 2003. Then the profit increased by 25% after that. So what we want to notice first is an increase or initial price. The initial year is not an issue right now. But another keyword is increased by 25% per year after that. So my initial price was $10,000. And then also, my next thing I noticed is that it increased. So my standard equation was when we were adding, here we had addition where it's a growth model. And it was by 25%. So my rate is 25%, which we can convert into a decimal. 25% is of this form here in decimal form. And then we can plug that in to write an exponential growth model. So we're going to be plugging in our A and our R, which is 25%. So we get Y equals $10,000 times 1 plus 0.25 to the T power. And then we can simplify that, combining our like terms in the parentheses. So it's Y equals 10,000 times 1.25 to the T power. So my first question was asking us to write an exponential growth model equation. This is that equation. The second part says, what was the profit of the business after 10 years? So now we want to know what T is, time in years. So we can do that by now substituting T in to solve for Y. So Y equals 10,000 times 1.25 to the 10th power after I substitute T. And I have solved this, but what you should know first off is that in order of operations, we will do the exponent first. So you need to do 1.25 times 10, or excuse me, to the 10th power first. Then multiply that by 10,000. That product would be $93,132.26. Also, cents. That doesn't look like a 9. This is money. I'm going to round it to the nearest tenths because that's what will make the most sense in this context. And then finally, it would ask you to write your answer in a complete sentence, and that would be your profit of the business after 10 years would be $93,132.26. Our next example, West Fargo's population is 35,000 people and increasing by 8% each year. So we should already notice some keywords. This is our initial population. We are increasing, and it's by 8% each year. So before I even move on, I'm going to write down the information I know. A equals 35,000 people. We are increasing, so it's going to be y equals a times 1 plus r to the t power. And we're increasing by a rate of 8%, which can be written as 0.08 in decimal form. That's 8 hundredths. And then finally, it says, what will the population be in West Fargo in 9 years? So we're going to want to plug in 9 for t years. So t equals 9 years. Now we can plug all these values in and solve for y. So that would be y equals 35,000 times 1 plus 8 hundredths to the 9th power. So I can simplify by combining like terms. 1 plus 8 hundredths is 1.08 to the 9th power. Now I can take my base to the exponent and simplify that. I have also done that step. So we have then once I've actually already solved the final product. So you would take that to the power. It'd be 35,000 times that number. So actually, let me do it on the calculator just to illustrate it. So it'd be 1.08 to the 9th power. Let's see. So that's 35,000 times 1.999. Then that product is 69,965 with a decimal. But since it's in terms of people, we're going to want to round it to the nearest person, the nearest whole number. So this would be people here. So in a complete sentence, it would be after 9 years with an 8% increasing rate of growth, we would have 69,965 people. So, and these calculations are usually pretty accurate. Okay, now in this example, they give us an equation here, and they're asking us to find what the initial amount is and what percent of the substance decays. So the amount y in grams of a sample of iodine after t days is given by, so it's a decay model. And since we know it's a decay model, because it says down here what percent decays, it's of the form y equals a times 1 minus r to the t power. And also, from our first lesson when we graphed these exponential functions, our decay was when b was less than 1. So since this is less than 1, it has to be a decay. 1 here represents 100%. So first, when we're looking for a, it's the same value. It's our coefficient out front. It's 50 in this case. 50 is a. So what is the initial amount of the substance? 50 grams. It told us the units. And then what percent of the substance decays each day? Well, we can set this equal to that. So let me be clear. We're setting this equal to this to solve for r. So that's 1 minus r equals 0.92. So subtract 1 from both sides. We get negative r equals 0.08. And it's negative, so divide by negative 1. R equals 0.08. And we want it as a percent. That is equivalent to 8% when we move the decimal place. So 8%. Also, you could do some mental math. We know it's a decay, so when 1 represents 100, what's the difference between 100% and 92%? 8%. But this just shows you that you can solve for r. All right. So again, now we are writing an exponential decay model that describes this situation. An adult takes 400 milligrams of ibuprofen each hour, H. The amount of ibuprofen in the person's system decreases by 29%. So the keywords we're looking for: 400 milligrams, that's our initial amount. Each hour, H is now that variable of time, and it decreases by 29%. So my equation is going to be y equals a times 1 minus r to the t power. A equals 400 milligrams, because that's my initial amount. That's how much we took. Each hour, H. So actually, when I represented t here, we can call that H, because that's my time, and it decreases by 29%. So the rate is 29%, which as a decimal is 0.29. And then how much is in the system of an adult after 3 hours? That would be our time frame each hour. But first we're going to write an exponential decay model. So y equals, A was 400 milligrams times 1 minus 0.29 to the h power. And then by combining like terms, we get 0.71 to the h power. This is our exponential decay model. Now, when we know what h is after 3 hours, so h equals 3, we can plug that in and solve for y, because then we will know how much is in the system of an adult after 3 hours. So y equals 400 times 0.71 to the third power. So we get y equals 400 times, I've also solved this, 0.35711, and then this product equals 143.16, and then milligrams is our units. This is how many milligrams is in our system after 3 hours. That is how you would phrase it in a complete sentence. Okay, finally, this is what you would have done if you did the extra credit activity. Write an exponential decay model, not that part, that describes the situation. The value of a new car purchased for $25,000 decreases by 10% each year. So we know it's decreases, so it's y equals a times 1 minus r to the t power. My initial value is $25,000, and it decreases by a rate of 10% each year, which is represented by 0.1. How much is the car worth after 5 years? Well, we know t is time for 5 years, so to solve for y, we can plug everything in. A was $25,000, 1 minus 0.1, and t would be 5 in this case. So y equals 25,000 times 0.9 to the fifth. Again, we take our exponent first, so 0.9 to the fifth. And then the product of that would be 25,000 times that, which is 14,762.25. Again, since it's in terms of dollars, we do want 2 decimal places, so the context matters. Now in this case, t equals 10 years, so we're going to substitute that in to see how much the car is worth after that amount of years. So y equals 25,000 times, this would be the same, it'd be 0.9 to the 10th power. And then when you take your exponent first and then do the product, you get 8,716.96. So you can see how quickly the value of your car is decreasing. When a starting value is 25,000, after 5 years, it's almost $11,000 less. And then by this point, it's less than $10,000. So the value of your car decreases very quickly. All right, Thanks for watching. Let me know if you have any questions. You can email me.